We have two speakers today. Hopefully you can see one of them. That is Magnus Smith. Magnus has been with the Fluke Health Solutions family for over a decade at this point, and during his career he has been our product manager and product specialist as well. He is instrumental in designing and creating many of the crucial products that we'll talk about today, as well as in the other portfolio that we offer. He takes the problems that you face or may not even know that you can see or face and turns them into technology so you can be empowered as an everyday hero. And our other, don't laugh at me, Magnus, I heard that. The other speaker we have today is Patrick Anderson. He has just joined us at the Fluke family here, and he is our product application specialist. He also helps a bit with tech and our very technical questions. So he's going to help us moderate our Q&A section. And no question is too complicated. I've put it as a personal challenge here. Let's see how we do, Patrick. All right. So Magnus, you want to take us away and get us started here?
All right, thank you. So glad to be here and to talk to you all today about some of the technologies that are being used inside radiation servo meters. My agenda for the day is we will start off with a bit of a context around where servo meters are being used, some of their main properties, and before we get into the different technologies. And I will look at ion chambers, Geiger Müller tubes, semiconductor diodes. I have excluded spectrometers and scintillator-based detectors in the webinar. A scintillator is basically, just to mention it, it's a material that emits light and when it interacts with radiation. And this light is then captured by a photomultiplier tube or a photodiode. And they come in various different models and shapes, just like many of these other technologies. When we look at all this throughout the webinar now, you will notice, and it really comes down to that, all of these have their pros and cons. And it comes down to how you utilize them and what application you need to measure on. At the end, we will also look at the RaySafe 452, which is a servo meter that actually combines two of these technologies to give it its performance that it has. And we end up with the Q&A session. And as Lindsay said, please fill out questions throughout the time, and we'll reply some during the time and some at the end. And when you are asking me questions, I will ask you questions. So my first question to you that I would love you to reply to is, in what environment do you primarily use servo meters? So hopefully you now see a poll. So I'll give you a couple of seconds here to reply. It's quite difficult to divide these into segments because there are so many, and we didn't have so many options to select from. But hopefully you can find some that fits you well. I'll give you a couple more seconds, then we move on. We are at 60%. There we go. Let's close it. I think you will now also be able to see the results. So it's a bit of a spread, but the majority is in the diagnostic X-ray or radiotherapy environments. Great to see. Some of these servo meters are being used in all these different areas, and that brings me to my next slide, which is servometers are being used wherever there is radiation present. So they are used to help people avoid unnecessary radiation. So you can test the environment to make sure that you are not being harmed, staff, patients, or the public. And it can be in the hospital segment to make wall leakage, tube leakage, radiation in the X-ray room. It can be for the nuclear medicine where you scan for spilled radiation isotopes, etc. For non-destructive testing, it may be in production lines to make sure that there are no cracks in molded parts or circuit boards, that the solderings are correct. Food industry, it's really a wide variety of areas where these are being used. And that's also why there are so big variety of different instruments out on the market. So I have another question for you right away. How many servometers do you use or have to cover your need today? So hopefully you see that question now as well. I'll give you all some 20 seconds or so. All right, let's share that data too. So there we go. Looks like it's a fairly good spread, everything from 1 to 2, 3, and even more. And I think you all have a good reason for it. It can be that one is really dedicated for this specific purpose, or you simply have two different applications that need two different servometers today. A lot to learn and much to keep track of and calibrate, of course. So I'll hide this and we'll move on. So what's important with a servometer? And it really comes down to your specific application, of course. Whether it's the high sensitivity, where it's easier to detect small variations of radiation. It could be a fast response time, so you can easily detect changes. And this is a quite common misunderstanding and a problem many feel is that what you see on the display on a very short pulse on most of the servometers that are out there is not always the peak in that pulse, because if you have a radiation present in your surrounding, it's fairly constant and it may change a little bit, whether it's background or a couple factors higher than that. But if you have a short pulse, like from an X-ray machine, that can be 100 milliseconds, 50, 10, even 5 milliseconds long. And it's difficult for many instruments to capture that and display that dose rate reading in front of you at the same time, because typically your instrument is updating the values once per second or 2 times per second or something like that. So what dose rate value did you get presented? Was it the one at the peak, or was it an average over the last second or last 50 milliseconds? So therefore, we always recommend, if you measure short pulses, to integrate and measure the dose at that time. And then you can calculate what the peak was in that pulse, since you have the pulse length. And if you do that, you will have much more repeatable values and readings, and you can even compare different servometers to each other as long as they measure dose. Some actually only measure dose rate, and then it can be a bit troublesome. But this is a quite big misconception and can cause some troubles every now and then. Good to think about. The dynamic range, whether you are measuring on low dose rates, if you need to go into the X-ray room, or close to a radiation source where you have higher dose rates, instruments may saturate and just give you a high alarm level. If you need both of those, you need an instrument with a wide dynamic range, so you can measure wherever you are present. If you are measuring inside the beam of an X-ray, for instance, then you need even higher dose rates. And then comes the wide or a flat energy response. And this is also quite important to think about when you purchase an instrument or think about what you are doing during your measurements. Because most servometers, or many servometers, are specified with help from an energy response graph. And that indicates how the instrument performs at a certain energy level. So if it has, here we have two different energy response graphs. The solid line, the blue one, it is fairly flat, and it displays, it shows that whether we are measuring on high energies, like cesium-137, which would be around here, whether it's on lower energies, diagnostic X-ray, it would still give us a value that is close to what it's expected, because it has a response of 1 throughout the whole range. If we compare that to the dashed line, the green one that is dropping a little bit here, it means that if we measure up at the higher energies again, we have a good response. But if we are measuring on diagnostic X-ray ranges, or let's say we have 40 kilo electron volt in our mean energy, we could simply underestimate the dose by a factor of 2. Just by looking at the reading of the display. So it's really important to think about this unless the energy response is flat, where you are supposed to measure. If you have a flat energy response, you never have to think about this. Apart from the radiological aspects, it could be good to value things like, do I save time with a fast start? Do I have a couple of seconds or minutes to go in between different patients? How easy should it be to operate? Am I using this on a daily basis, or am I using this on a monthly or a half a year basis? Then I maybe need to relearn every time. So the easier, the better normally. Sound upon radiation could be really beneficial. Then you can hear whether it's radiation present or not. Some instruments have the possibility to save and export data for reporting, which can be great if you need to provide that to the hospital or the clinic or your customer. Then, of course, more physical aspects, whether you need it to be waterproof or durable, the size and weight, and then what quantity you are measuring, whether it's rad, Röntgen, Gray, Sievert, REM counts, becquerel per square centimeters, and so forth. So it's a lot of things to think about when you acquire a servometer. With all this said, we will now get into ion chambers, and I will go through that. So an ion chamber is a gas-filled chamber, usually by air, with a voltage applied across 2 electrodes, which create an electrical field. So the ionizing radiation then ionizes the gas and forms ion-electron pairs, which create a current. And this current is what we are measuring to create a corresponding or proportional current to what the radiation is. And this is very straightforward and the basic principle of how you define radiation, more or less. So very simple in that aspect, and they come in many different shapes and forms. So how can you increase the sensitivity of one of these? So either you can increase the size. With a big chamber, you have more volume of air to ionize and a bigger chance to have a higher current that you can measure. So therefore, you have a higher sensitivity in the chamber that is bigger. This, on the other hand, makes it a bit more bulky and maybe even fragile, depending on the design. And you also have a risk of partially irradiate the chamber. If you are measuring on a small or narrow beam, you may underestimate the dose unless you irradiate the whole surface of the ion chamber. Another way to change the sensitivity is to use a pressurized ion chamber. So here we have the same volume, but we squeeze in more air. And again, more air generates more electron pairs that can generate this current that we measure. So this typically makes it more robust, but to the cost of having a high pressurization can cause it to be classified as a hazardous material, which is cumbersome when it comes to shipping the products with air transportation. Another thing is that you may lose response in lower energies, just like we saw on the two energy graphs before. Because when you have a thick ion chamber wall, that wall prevents low energy radiation to penetrate the ion chamber. So this is why the dashed line here most likely comes from a pressurized ion chamber. The vented chamber, that has a more flat energy response normally. And depending on the design, it can also detect the beta radiation if you have a thin enough window for it. If we look at the Geiger Müller tubes, they are also an enclosure with a gas inside. It's a combination. The exact formula of the gas varies a little bit, but it's a gas-filled chamber with a high voltage applied across two electrodes. In this case, the radiation causes an avalanche inside the chamber. So everything gets ionized, and it creates a count upon radiation. So instead of a current that we got from the ion chamber, we get a pulse every time the GM tube gets hit by radiation. And this can, during that time right after this happens, the GM tube becomes blind to radiation for a very short period of time. And this is called the dead time of the GM tube, which is typically corrected for in instrument design when you use Geiger Müller tubes. So this is just an illustration how the signal from these would look from a development perspective. This is nothing that you will see as the end users, but when you capture the radiation from an ion chamber, you get a current that is proportional to the dose rate. So a higher current with a higher dose rate. A low dose rate creates a low current. With the Geiger Müller tube, on the other hand, it's with a high dose rate, you have many pulses, and with a low dose rate, you have fewer pulses, but they all have the same amplitude. So in that aspect, they are quite easy to count in that sense. All right, Geiger Müller tubes also have, they come in so many different shapes as well. The one we are looking at right here is one that is called a pancake probe, or it has a very thin mica window, so it can also detect beta radiation and some alpha radiation. It comes with a very fluctuating energy response. So at energies around 50, 60, 70 kilo electron volts, it over responds by a factor of 4. So it's not so good for quantifying the radiation unless we compensate for that with filters. But it's really good for detecting radiation at these energies, which is of course great for that purpose. And that's why many of these are used for finding contamination or finding wall leakage, etc. Then if you want to quantify it, you may use another probe or another instrument or add a filter to get the correct leakage. And then we come to semiconductor diodes. And they are used, they come from, it's a solid material, typically silicon. And they are naturally more robust. There is no ion chamber walls, there is no air that can leak out, etc. And they are very small. And when you irradiate one of these diodes, it interacts with the crystal and it produces free electrons, and you can measure that current. So same principle, but in a whole different design. And with silicon sensors and semiconductor diodes, the sensitivity can be up to 1 million compared to that of an ion chamber, same size. So therefore, you have the potential to create a very, very small detector. Semiconductor diodes, they have an energy dependence built into them. So we need to compensate for that one way or the other to create that flat and nice energy response that we all want to have. So by doing that, in order for us to do that, we use several channels with diodes. In this example, we have 4 channels, and we add different amount of filtration on top of these different channels. That way we get 4 signals that we combine during the measurement, and through that we add them together and which gives us a nice and flat energy response. Compared to the ion chamber or Geiger Müller tube, which only gives us 1 signal. The ion chamber provides us with 1 signal, which is the current, which corresponds to the dose or dose rate. The same with the GM tube, the pulses or the counts corresponds to dose rate or a dose. When we have 4 signals, we can actually utilize them not only to calculate the dose and dose rate. For diagnostic X-ray, for instance, when you measure in beam, it's really valuable to get the HVL, which is a half value layer of total filtration. And that can be calculated automatically with these different channels. For a servometer, it can be helpful or useful to get the mean energy, for instance, in the radiation. It will not be a spectrometer in that sense, but we can get some of this data out from the signal. What we have looked at here is the ion chambers It's not necessarily wide dynamic range, but it can have a very wide dynamic range, especially if we compare it to the Geiger Müller tubes, which typically have a more narrow dose rate range. For the ion chambers, you need to think about the size versus sensitivity, a big chamber versus a small, or the pressurization versus sensitivity. And also, if you have a pressurized one, you may lose or you will lose response at low energies if that's where you are performing your measurements. So really something to think about there. The GM tubes, they have a high sensitivity, but less limited dynamic range, fast response time typically, and we need to compensate for the dead time, which is also done internally. And for the semiconductor diodes, size is really great here. They are very small, they are durable. We can provide a very wide dynamic range. They have a fast response time. They do have some temperature dependence, which needs to be accounted for during the development of these type of instruments. But what if we wanted to make that perfect instrument? Would it be one with a wide dynamic range, with a fast response time, that was durable, and it was small, and it had all these things that we've looked at, the pros from the different technologies, and that's one thing that we've looked at now from the 452 perspective. But before we go there, I would like to ask you this last question. I hope you're continuing to ask us questions though, but I will ask you one more question here, which is, what technology does your current servometer have? Maybe you don't know, and that's totally fine, because the best servometer is the one you don't know about what technology it has. It does the job, and that's it. So I'll give you a couple of seconds here. Take a break. All right, let's stop it there. I see some more results coming in. You have 5 seconds. 4, 3, 2, 1, stop. And as expected, there's a lot of ion chambers out there. A good amount of semiconductor diodes, some scintillator based, and others or don't know. But again, I think all of these have their place in your portfolio, perhaps, depending on your different measurement needs and applications. So this is just great information, and we all see that all sorts of servometers are being used in the field. I'll hide that again, and would like to give a short introduction to the RaySafe 452, which is actually an instrument that combines semiconductor diodes and the GM tube, a pancake detector. And we have placed the GM tube in the middle. I'll put these out. And we have an array of diodes in a circle around them with different filtration, as I explained, so you can compensate for those different energies. So when we have low dose rates, the GM tube is really good. It is fast, it is stable, and so. But when the dose rates increase, a GM tube typically saturates after a while. And long before that, we have automatically switched in the diodes, which have a very wide dynamic range. So we can measure from the lowest, what we call the background radiation levels in that sense, up to very high, up to 1 sievert per hour with this instrument. We have two different filters, lids that we apply in front of the instrument. So one filter is for air karma. It's the gray one here, which measures in gray, rad, or Röntgen. So, and this is the filter that compensates the energy response of the GM tube that I explained earlier. So instead of having this high energy dependence of the GM tube, we compensate that with this filter. And the same goes for the ambient dose equivalent filter, where you measure in sievert or in rem, where we also compensate the GM tube in that sense. The solid state sensors have fixed filters already, and those filters are built into the design and automatically adjusted inside the instrument. But the GM tube, since that only provides us with one signal, we need to add these manual filters on top. If you remove the lids from the instrument, you can also measure with the GM tube as a bare pancake, and then it becomes that great instrument for sweeping surface to find contamination or radiation with that high sensitivity at 50, 60, 70 kiloelectron volts. And when you have found something, you can add the lid again and continue to measure to get the correct dose rate in there. So with this combination, we believe that we have created this instrument that actually has a high sensitivity, and it has a fast response time with a wide dynamic range and with a nice and wide and flat energy response. So, which makes it a very versatile and broad instrument that could do possibly a couple of these things that you are measuring today. So if you were one of the persons who answered 2 or more or 3 or even more servo meters in the beginning there, perhaps 452 could help you out and let you get rid of one in your shelves. Apart from the measurement technology and measurement performance, it is really fast to start up. Some servo meters take a minute or 2 to start up. This one is up and running in about 10 seconds. It's really easy to operate. You can turn on and off the sound. It automatically saves data always, every second. The dose rate data is stored every second for you, which you can export for analysis or for reporting. It is IP classified for weather protection, for rain and dust. It's lightweight and it's a small size. And if you have these different lids, you can switch between rad, gray, sievert, rem counts depending on your application and need. Of course, maybe you don't need all of these different quantities, but having that possibility in one device can be really valuable. So to finish off, I just want to share the range of servo meters that we have in the Fluke Biomedical and RaySafe portfolio, and to show that we have basically all these different technologies in our instruments, and they have their different purposes. So we have the 452, which I just talked about. It's a combination of the GM tube and semiconductor diodes. we have one that is called the X2 survey, which is only semiconductor diode based. The 451P and B versions are ion chamber based, one being pressurized and one being vented. And then we have the ASM 990 or 993, which is a GM pancake based detector. No longer available in Europe, I need to express that. And they have the different places in the at you as an end user. So very versatile, very broad range, these 452 and also the 451. The X2 survey is specifically made for the diagnostic X-ray room to measure tube leakage and wall leakage and stray radiation in the room. So it has a more narrow energy range than the other ones. And then the ASM 990, which basically can be used to find spilled contamination, which you can also do with the 452 now.